Okay, so this is joint work with Pat. This builds on work with Ben and some other people who have contributed to this research I have mentioned at the bottom. Okay, so what's this? So this motivating example is from the paper. So the idea here is that humans, we understand many social interactions with little effort. If you take a simple example that there are two people, Abe and Bob. Abe has some cash, Bob has a car. Well, sometime later, we hear that Abe has the car, right? So now we have not observed any transaction. One hopes it has happened, but we have not observed it. So two reasonable explanations have come to mind. One is the nice one, that Abe bought the car from Bob using this money. He paid him for the car. The second one, not so nice, but possible, is Abe stole the car from Bob by threatening him. So we also know that these two explanations are mutually exclusive. And later on, if we happen to hear that Abe gave the money to Bob, then we eliminate theft as an alternative, right? So what we want in this line of work is a theory of such reasoning ability. And we look at the corresponding abilities that humans exhibit when they make observations, right, and try to explain them. So they explain these events by connecting them through knowledge that they have. They introduce plausible assumptions about unobserved events, like we saw in the previous example. So they incorporate these observations into these explanations incrementally, as in we do it, and detect inconsistent beliefs to address any conflicts that come up. And the last bit is to generate alternative explanations of these observations. So these are distinctive features of human level intelligence and considered as natural targets for cognitive systems research. And that's the general attempt of this line of work. So the first difference here is from traditional formulations of abduction, where we introduce these assumptions. So the classical treatments, they treat abduction as proof of abduction. They construct proof graphs. The observations serve as the roots, and the observation assumptions are the terminal nodes. And in this work, in this paper, and the prior one, this is referred to as derivational abduction, because the observations must be derived from these other beliefs, right? But the view that's taken in this work is a different one, that what is called associative abduction, or Pat likes to call it a guilt by association, in the sense that here the construct proof graphs, but both the observations and the assumptions only appear as terminal nodes. And then you have these other derived nodes that appear above, as shown in this very simplistic diagram. So this is called associative abduction, because the observations are explained if they hang together, if they make sense put together, right? So that is what is the approach that is taken here. And so the theory of associative abduction, which was initially introduced by Ben and Pat in a 2019 paper. So it incorporates certain structural postulates about the representation and organization of explanations. And it also introduces certain processing postulates about mechanisms that generate and revise these explanations. So this is what I'm going to go through next. There are 5 of these structural postulates and 3 of these processing ones. And basically, this theory comprises these postulates about the cognitive structures and their interpretation. And there is also a system that instantiates this theory in a sort of architecture, which I'll mention briefly later. But these are conceptually distinct, right? So I'm going to start with describing the postulates themselves. So item 1. So there are 2 types of knowledge, complementary types of knowledge. The first one is the so-called definitions. They specify high-level predicates as conjunctions of simple ones. So you could have, in our sort of motivating examples, a higher level definition of what purchasing or robbery mean. And then you could have lower level rules for the transferring of property, right? In this case, like, paying the money, or like, robbing the other person. So it is similar in organization to a logic program for those who are from that field. So you would have like, a body and a head, and it's also similar to a context-free grammar. The second kind of knowledge, of course, is the constraint. So this specifies relations that are in some sense mutually exclusive. In our example, for instance, Abe cannot or should not be buying and stealing the item at the same time. So it in some sense indicates inconsistency. When these two beliefs are jointly satisfied, it means that this can't occur, and this is something that needs to be then resolved. So in essence, the definitions, definition rules are generative in nature, while the constraints are restrictive in nature. Okay, that was the first one. The second, in terms of the structural postulates, is that there are 3 types of beliefs. They're all in dynamic memory. So there are three kinds of elements in the short-term, in the dynamic memory. The first one is the observed beliefs. So these come from external perceptions, so you observed Abe with a car, so Abe has possession of a car. The next one is the abduced beliefs. These come from introducing assumptions, which you do to take care of these unmatched antecedents of the definition rules. So, and the third one are the derived beliefs. So these are deduced from other kinds of beliefs using knowledge, right? And again, one can easily construct examples of these in the motivating example that we have seen, right? And let us a couple of them in this slide as well. So then the beliefs take the form of ground literals, and they are predicates with 0 or more arguments. And what we have is these three kinds. Okay, so let's try and remember that, like 2 kinds of knowledge, 3 kinds of beliefs. What do we have next? The structure of explanations themselves is that you have these instances of these applied definitions, which are we call justifications. These are stored and organized into higher level explanation. So an explanation thus is a connected proof graph that has 4 elements. It has a set of observed beliefs O that are to be explained, and these are the, as we saw before, the terminal nodes. You can have a set of abduced or assumed beliefs, and these are also terminal nodes. Then you have the set of derived beliefs that follow from your O and A, that is from your observed beliefs and the assumptions you have made. And last bit is the justifications that essentially, instances of this rule application. And these show how the derived beliefs follow from the observed beliefs and the abduced beliefs. Right, an example that is used in this paper repeatedly and which makes sense is the notion of parse trace. So in which case your observed words would be the terminal nodes, and the non-terminal nodes would be derived, and you would have different parses providing on the basis of different justifications. So an explanation in a sense can have more than one derived node, but it must be connected, right? So in this simple, again, diagram, you have the sort of root nodes being the observed or the terminal nodes being the observed or the abduced nodes, the assumed beliefs, and the other ones are derived, right? So once again, the key distinction here is that the observations are terminal nodes and not root nodes, as in much of the work in abduction. Okay, that was the third one, the structure of explanations. The fourth one is about possible worlds. So because explanations are stored as sets of justifications and beliefs, these are represent possible worlds. So justification can contribute, of course, to competing accounts, right? You can have 2 parses of a sentence. They can share subtrees, and each can be associated with multiple words. So worlds are in essence organized like a phylogenetic tree that traces their evolution over time or over several steps. So the root node, once again, is the initial set of beliefs. And then when you branch off, each child omits some elements in its parent word in order to sidestep some inconsistency that has been observed. And the terminal nodes, hopefully, denote words that are consistent with both observation and knowledge. Right? So we can thus talk about 2 kinds of words, closed words, that contain known constraint violations. And then you have active words at the frontier, which are, again, internally consistent. Right? And then if you have siblings, they can, in some sense, they offer competing explanations for your observations. Okay, now the last one is that there is the distributed representation. This is probably clear already, but I'm just going to reinforce this. So beliefs are all stored in one working memory, but each element or each belief, it specifies worlds in which it does not hold, right? And this is done as a computational efficiency consideration, in the sense that alternating words are encoded in a distributing manner. So it takes advantage of the shared observations, abductions, derivations, and so on. And it avoids repeating the same inferences during reasoning. And in some sense, this supports implicitly a form of parallelism. So by storing worlds where beliefs do not hold, it reduces the memory load, and provided, of course, that elements held in common are the majority, right? So this serves as a heuristic measure that has no guarantees, as with many other heuristics, but it's often believed to be effective, right? And so this is the 5th of the structural postulates. Let's now look at the processing ones. First one is that of incremental processing. So explanations, they process the process of explanation. It alternates between 2 different cycles. The first, or the outer loop, if you want to think about it, is the observation loop, which accepts the inputs from the environment. And this could be, say, from a camera image, this could be speech. In any sense, it processes this and produces these new observed beliefs, right? The inner or inference loop uses these observed beliefs and now says, okay, I'm going to have to extend and revise my explanations to account for these observed beliefs. So it repeatedly goes through this process of selecting a focus beliefs, invoking definitions to elaborate these explanations, right? These generative ones, and then you use constraints which are restrictive to detect and repair inconsistencies, right? And this is a process that goes through repeatedly. And the focus belief that you pick in some sense also determines the knowledge that is relevant, right? So you're only going to look at the definitions or the constraints in which at least one antecedent unifies with this focus belief. So you produce the derived beliefs and the abused beliefs, and you construct the explanations incrementally, but it is done bottom up, right? So this is the first of the processing postulate. The second one is that there are two varieties of inference. So explanation relies on two forms of inferential processing. One is this elaboration, and this involves, as mentioned earlier, an application of a definition. So it produces a new belief based on the rule's head. And in order to get there, you may have to add assumptions if some antecedents in the rule are absent, right? This is the abduction bit. The second kind of inferential processing is repair. So this is used when you detect a violated constraint, right? So where you say B1 and B2 should not happen together, right? So, and then you eliminate it by deactivating each world in which this conflict is detected. And you generate one child with B1, another with B2, right? So the new world retains beliefs from its ancestors that are at this point not responsible for or implied by the removed beliefs, right? So the inference alternates between elaborating words, which is a monotonic process that adds to it, and spawning words to fix inconsistency. And this is the non-monotonic bit. Okay. The third of the processing postulate is the focus of attention bit. So the explanation construction is helped by knowledge, but is driven by the observations that are obtained incrementally, and which is these are the observations that the system has to account for. So of course, for each observed fact, multiple accounts are possible. So you have to search through the space of explanations consistent with the data. And the explanatory inference relies primarily on the focus of attention to provide the heuristic guidance. So as I mentioned before, you're going to have to select a particular belief to focus on. And during elaboration and repair, you only consider definitions and constraints whose antecedents has an antecedent that unifies with F. So because the worlds are encoded in a distributed manner, each inference step can elaborate and repair multiple worlds that share that belief. And you have this notion of like a stream of consciousness or a spreading of activation in which one idea leads to the other. So this mechanism essentially makes the retrieval or matching more tractable, but it can, of course, overlook useful inferences and can also have inconsistencies, which we'll have to deal with. Okay, so this whole theory was implemented in the PENUMBRA system. So this is an architecture for explanatory inference that builds on Umbra, which is a previous one with, again, Pat, Ben, and others, an earlier system for abductive explanation. So like most cognitive architectures, this has a syntax for knowledge elements and working memory. It has an interpreter that operates over these structures. And it also offers a programming language that makes certain theoretical assumptions about how the mind operates, right? But this is in an earlier paper. So the purpose of this paper was to try and see if the theory that we have of this abductive inference, this can be scalable, right? So that was the main analysis focus here. So both analytically and empirically, try to see if the we can achieve scalability, right? So the first thing to do was to parameterize the performance using some variables. So you took the processing times of inference cycles, different stages of that. Again, the key stages are selecting the focus belief, checking the constraints, and selecting the definition rules to apply. So you had specific parameters. I'm not going to go through this in much detail here. These are listed and described in the paper, and also to parameterize the relevant factors and some sort of independent count variables that we will use for the analysis. The first thing that is described in the paper is an analytical computation of the costs of inference. This is the how we come up with these equations are described in the paper, but these then serve as hypotheses for the experimental evaluation, right? For instance, the three main things as we talk about here in terms of the cost of inference cycle is the time for selecting the focus belief, which has in some sense a linear relationship, the time for checking constraints, again, a simple relationship, but the most computationally expensive bit is the time for selecting the definitions, and this is exponential, right? And it's exponential in this parameter a subscript d, which is the number of antecedents per definition, right? So what we then did is we say, okay, let's take the most computationally expensive bit, which is the selecting the definition, and let's compute empirically the cost of selecting this definition for elaboration of the explanations, right? And we use synthetic data sets. These are relatively simple data sets. The paper describes them, again, in the context of sentence parsing and otherwise. So I'm going to, in the time that's left, I'm going to talk about the results at a sort of, not at a finer granularity of detail, but we can talk about questions and other things after this is done. So the first hypothesis that came, again, directly from the analytical derivations done, was that the processing time per definition selection is independent of the number of definitions. It's a, and that's what we did. We fixed certain parameters like the number of antecedents per definition, the number of definitions per predicate, and the number of beliefs per predicate. And then we varied the number of definitions, as you see on the x-axis, and we took a look at the compute time on the y-axis, and this is reasonably meets the hypothesis that we had. The second one was that the processing time per definition selection is a linear function of the average number of definitions per predicate. And so what we did there again is we fixed the parameter b subscript p, again as in the first experimental 3, and then what we did is we considered different values for a subscript d, the number of antecedents per definition, and varied the d subscript p, which is the number of definitions per predicate, which is what we wanted to check. And then we measured the dependent variable, which is again CPU seconds per cycle. And again, this also seems to bear out. This is a linear function, though the increase is more in one or two of the combinations than others. The third one, which is looks at the exponential function, is that the processing time per definition selection is exponential in the average number of antecedents per definition. And again, we fixed one of these parameters, which is b subscript p, varied different values for d subscript p, and then the a subscript d, and measured the CPU again seconds. And again, we see here that the experimental results, at least in the context of definition selection, are consistent with the analytical calculations. The processing time grows slowly for the n subscript d, d subscript p, and b subscript p, and it's exponential in the a subscript d, which is the number of antecedents per definition. This is due to the need to consider partial matches, but this can be bound by limiting the number of antecedents per rule. And this also, in some sense, indicates or motivates us to go towards the hierarchical organization of this knowledge. Okay, how am I doing on time? Not bad. Let me keep going. Okay, so that was good in terms of the experimental results, empirical ones matching the analytical results, at least in terms of the time for definition selection. But what we are interested in is, of course, the full explanation needs to be scalable. And we need to explore scalability. But in this case, a primary thing or important thing for us was to explore scalability to the number of alternative explanations, right? So human language processing also indicates that the use of effective heuristics guides choices, and we are quickly able to arrive at the best explanation while disregarding all the competing ones. So in this case, the penumbra heuristics, of course, are there in the context of selecting the focus beliefs and definition selection. So the hypothesis we came up with was, given effective heuristics, the time to find the best explanation is independent of the number of consistent words. So if you have many options, you can still find the best explanation as soon as possible. Now, the context of, if you want to talk about the best explanation, you have to first say what this best explanation is. And there have been many different ways of describing this in the literature. So you could look at simplicity, coherence, summed weight of assumptions, in a probability of parse trees, and so on. So we use a variance of a particular approach by Hobbs et al. And what we do essentially is we have a heuristic for selecting the recent beliefs, and you have another heuristic that selects rules with higher scores, right? Essentially, these are the definitions that you want to elaborate on. Okay, so this is by itself is not sufficient. You need some kind of a search process through the space of explanations. And in this case, we need a depth first search through the space of explanations. And you apply definitions that elaborate on the most promising word before others, right? Occasionally, this can take you down the wrong path. This is to be expected. But overall, the hope is that that will not happen as much. If of course, we have good heuristics and this hypothesis holds true. So this is one instance where we once again went back to the parsing, sentence parsing task, where these parsers map to the explanations. The terminal nodes, as mentioned before, are the words. The root node is the root of the explanation, and these different parsers are set up to have different scores, so you can actually run this evaluation, right? And as what we measured is basically the number of cycles it takes to find the best parse as a function of the number of consistent explanations or parsers that exist. And as I said, these are set up to have different scores. And what we wanted to do was we wanted to compare against the random selection of the focus belief and or the rules. And of course, this should not work well because this random selection should not work well as the heuristics. But this is one instance where the empirical results don't necessarily match up. So what we find is, except for this one instance close to the end, the last point here, for a high number of consistent explanations, where it drops, which is promising. But what we find is if you just compare both these heuristics, both for the selection of focus beliefs and the selection of the rules, if you use both these heuristics and you compare it against just one heuristic, right, where one, for instance, this one is just selecting the most recent belief, or selecting only the rule that has the highest score, they seem to have similar growth rates here. So that is not very promising. And this is something that needs further exploration. Okay, so I'm going to wrap up now. So the explanatory inference approach described here borrows ideas from a lot of prior work. Again, some subset that is mentioned here. The approach basically builds on these traditions, but tries to combine them in novel ways to explain the explanation process. Overall, what we have been able to show is a computational account of explanatory inference with two forms of knowledge, three types of dynamic beliefs organized as linked justifications that are associated with one or more words. We have three mechanisms that are basically focusing attention on a particular belief, applying the definitions, and repairing constraint violations. And we implemented this in this theory in PENUMBRA, and we conducted a scalability analysis and empirical evaluation, of course, with synthetic data. The processing time scales well, except for one particular parameter, but this is something that can be bounded. And we also have in the paper qualitative hypotheses about the ability to find best account before alternatives. And the heuristics we had was, their description or the definition was based on the understanding that these would lead to benefits towards finding the best explanation before others. But this is not what has been borne out by the experimental analysis. This needs to be looked into in more detail. And that is one thing we plan to do. Look at criteria for explanatory quality and heuristics, and look at these other popular ones and see if this can be used to analyze the last experiment better, and also explore scalability to more complex problems, and overall try to get a fuller account of explanations. And with that, the end. I think I'm on time.
Very good. Oh, absolutely, absolutely. So questions, please.
Yeah, have some troublesome questions for Pat.
Well, Pat says that if nobody else has questions, he will ask some. But let's first hear whether some non-co-authors would want to ask questions. Okay, well, Pat, it's all yours for now.
Okay, I'll try. So Mohan, when this is the second round for this paper, last year when it got rejected, one of the reviewers really pointed out that this is very similar to work on truth maintenance systems, which we acknowledge in the paper, but that those scale to very, very large sets of knowledge bases and so on, sets of rules, and we're not doing anything like that. And I think that they really misunderstood what the goal is. But do you have any thoughts on this? I mean, we did have fairly small experiments. We're not scaling to really large things. Do you see any problem with that? Do you think that it's
No, okay, Pat, we've had this discussion before. Okay, so I don't think so. I think this shows this. I think the main thing here is the way in which the explanations are constructed and how they are expanded. I think that has promise, And I think that's what we are trying to study here, is if this theory has merit in coming up with good explanations. Whether it should scale to larger databases, well, that would be nice, but we have not tested it yet. It would be nice to do so in the future, and we accept its future work. But I think at this point, just seeing if coming up with this effective heuristics and seeing if we can figure out the best explanation first would be the
well, yeah, or on average, you find a good explanation.
Correct. Yeah.
I mean, the history of work on abduction is people, I think, mistakenly try to define it as inference to the best explanation.
Yeah.
Implied optimality, and of course, as a Simon student, I don't think that that's a very wise path to follow. And I hope we'll hear more about that from our invited speaker.
May I jump in here, because it's really, well, okay, I don't know whether this is a part of your theoretical work, but, well, explanation, it's operation to best available explanation. But listen, your motivating example is incomplete, because the choices are not just two. If you take into account joint ownership, okay, so the system doesn't have this knowledge, and then it selects something. But is there any desire to incorporate in the theory in the future the ability to expand this basic knowledge from interaction, from whatever, when in fact it didn't buy, didn't steal, but always co-owned the car? I forget the names of the people. Do you see what I mean?
Certainly, we are very interested in extending the model by learning, and we have specific ideas on how to do that, but not the kind of that you're talking about. You're talking about adding a knowledge that somehow overrides a constraint, right? So you have these things.
No, Pat, I don't think so. Sorry, Sergey, go ahead. Yeah.
Go ahead, Mohan.
No. Go ahead.
Well, we have a constraint. Only one of us can talk at a time.
Okay.
No, I'm not going to argue that, but go ahead. I thought Sergey did not necessarily mean that, but go ahead.
Well, I think that's the most interesting one, because we hadn't thought of it. That is, you believe that two things can't happen at the same time, and then you realize, well, no, they really can under these special circumstances. That's almost, so the kind of learning we've talked about is adding new definitions, right? And we've thought about how you might learn constraints empirically, but not how you might decide that constraints that you had hypothesized are actually not. After all, it would be a non-monotonic learning of non-monotonic knowledge, which is ironic.
Okay, but in practical applications, one has to expect this type of situation that I just exemplified. Anyway, right.
Sergey, I'll give a slightly different answer. I think it might be, it's not something we have thought about, but might be interesting to think about, I think. Yeah.
Yeah. Absolutely. All right. So if there are no more immediate questions, then let's thank Mohan and Pat. And this is the end of the first session. Yeah. Yes, Henry, we are applauding. Thank you very much.